Our next speaker is Philip Withers from University of Manchester, and among many things, he is a world-renowned expert on X-ray imaging. So Philip will talk about this today. Thank you.
Thank you, and I think it builds a little bit on some of the really exciting work that Stephen was showing in the last talk, and my aim here is also to just provide some general introduction, because of this is at the beginning of this really exciting a few days. So I thought it was a good time to just give some basic introduction for those who are not so familiar, and also to then look at some of the key aspects that you can interrogate with X-ray imaging. Just a few comments. My work is partly funded by the European Research Council, and I represent here we have a collaboration in the UK between a number of universities led from Sheffield on advanced manufacturing using powder processes, something called MAP. We actually have our quarterly meeting over the next 2 days, so some people will pop in and pop out, I suspect, but we're trying to juggle multiple meetings. But it's really about looking at additive manufacturing, and also near net shape hipping and other powder processing for metallurgical, for making parts from metals and alloys. And is a 5-year project, has 5 years to go. So that's a major aspect in the UK. And also I represent the National X-ray CT facility, which is a EPSRC, that's Research Council funded project to make available X-ray imaging for academic and industrial research. Okay, and I obviously today I don't need to explain to you the value of additive manufacturing in terms of the architectural flexibility that you get when you use powder processes, additive powder processes or wire processes. It provides us with the opportunity to have tremendous geometrical freedom in the external shape, but also on the internal structure. And so it's important that we're able to validate and qualify and to quantify those structures. And in many cases, and certainly in biomedical applications such as the one shown here, you can exploit additive manufacturing to create complex structures which are ideal for biomedical integration. And one has the freedom to grade materials. One has the freedom to have different materials on the outside, or to have different structures. Now, following the first lecture, I guess it's just useful to just stand back and say, well, how does CT work? Computed tomography, usually you rotate the sample. At least in material science, you tend to rotate the sample. In medical science, you tend to rotate the scanner and leave the person stationary. But in material science, one tends to rotate the sample and collect a series of projections. And those projections are usually one might acquire between 500 and 3,000 projections. It depends a little bit on the resolution. It depends a little bit on the number of pixels in the detector, but basically somewhere between 500 and 2,000 or 3,000 projections. In some cases, when one wants to go very fast, you might reduce the number of projections, in which case you generally need special reconstruction algorithms to recover the kind of quality that you might want. Here you can see a shell. I think a shell was the one. I think one of the first things I put in our system in Manchester over 20 years ago. And I think I was remembering back to when I was a child and I watched a film called Dr. Dolittle, which was all about a man who could speak to the animals. And I remember he traveled inside a big seashell, and it was always very exciting to see those first images inside those seashells, just like when I was a child and watching Dr. Dolittle. We wrote a primer recently on X-ray computed tomography, and that's downloadable from Nature Review Methods Primers. So if you just want the basic introduction to CT, that's a good place to start. There are some important issues with CT. Generally, you scan the whole sample. So generally, the width of the sample determines the resolution, and the number of pixels that you, because you normally have somewhere like 2,000 or 3,000 pixels in your image, that means that your resolution is something like 1 to 2 pixels, or maybe 2 to 3 pixels. So your spatial resolution is generally around 1,000th of the volume or the dimension that you're scanning. So if you're scanning something that's about 1 millimeter in size, you can get 1 micron resolution. If you're scanning something that's 10 millimeters in size, you would have 10 micron resolution. And clearly, as you move to larger and larger additively manufactured components, generally the resolution falls. There are some ways of getting around that with region of interest tomography, but it's generally a good benchmark to say that you can get about 1,000th of the dimension. The resolution is about 1,000th of the dimension of the sample. As I said, in the UK, we have a national research facility, and we have 10 different scanners, and also we use synchrotron scanning, just as Stephen showed. We have some free at the point of access funding, and we can make some time available to people from overseas as well. But generally that's for short studies. And then we have longer access through daily beam charges where people can apply and can use our facilities on a daily rate. And if anyone is interested in accessing those facilities, they can access those via the website nxct.ac.uk. I just thought to give a bit of an overview, it's helpful to plot tomography timescales on one side against spatial resolution on another. And synchrotron beamlines, as we've already seen, can work at very, very fast acquisition rates. And since we normally, as we saw in the last talk, you can have acquisitions of each projection in fractions of a second, maybe a millisecond or so. And so if you need 1,000 projections to make an image, that might be 1 second for a tomograph. But of course, remember that in a synchrotron, you're rotating the sample. So your sample is also rotating at 1 second, once every second. And so there are some geometrical restrictions to the time at which you can take tomograms. Of course, you can also take radiographs, as was shown in the last series of slides, where you can get that individual frame rate. But basically, for fast studies, you tend to need synchrotron beamlines, but for slower studies, you can see here at nanoscale, you can do, we have a scanner that will achieve 50 nanometer resolution, but the scan speeds might be 1 scan per day, so much slower than at a synchrotron. Similarly, at the micron scale, it might be a period of hours, and then at the meso scale, where you might be looking at tens of microns, you can do scans certainly in minutes, if not fractions of minutes. And so it does present the opportunity for scanning a range of additively manufactured parts. So I'm going to start with real-time imaging using synchrotron X-ray radiography, and I think I will I'll go through this fairly quickly because I think Stephen gave us some really vivid examples of what you can do with X-ray radiography. As he showed, you need some kind of simulator system. This one is the one developed at University College London by Peter Lee and Alex Leung. But you need a system that will allow you to additively manufacture on the beamline, in this case using a laser. And you scan the laser, as was shown in the last talk, and the powder generally sits between two windows, in this case boron nitride plates, as you can see in the bottom inset. And then you get an image on your detector. And by scanning the laser beam across your sample, you can collect a series of radiographs to create a two-dimensional movie. So just again to show the kind of things that you can see, I think these samples tend to show individual the melt pool slightly differently from the last talk, but the basic technique is just the same. Here you can see the molten pool, you can see the powder, and the laser beam is moving from the right to the left. And you can see the kinds of images that show the extension of the melt pool. You can see spatter of powder particles. You can see entrained gas bubbles. So you can see many of the aspects that many aspects of additive manufacturing that threaten the integrity of manufactured parts. And you can understand how control of the laser power, the translate velocity, the powder size, and various other aspects can be used to control the quality of the additively manufactured part. Similarly, you can see when you get, if you travel too fast or the energy is too low, then you will end up with a discontinuous track formation. And there are plenty of other defects that you can study using X-ray radiography. You can see here that these are images taken over fractions of a second, and you can see, for example, the loss of powder, and you can track those in real time. So there's much to be gained by imaging in real time in radiography, but there's also an awful lot to be a lot of value from slower time scale X-ray CT done either in the lab or at the synchrotron. And I want to give a little bit of an insight into some of the things that you can do using lab CT. Of course, the first thing is that you can qualify and quantify the accuracy of your part. And here is a little video from Anton du Plessis in South Africa, which shows that part I showed at the beginning. And using CT, you can accurately measure the internal diameters, you can measure the external diameters, and of course you can measure the lattice work. The image on the left shows the kind of defects that you often see when you make lattices. You can see adhered particles on the surface. You can see a sort of knobbly structure due to the definition of the additive manufacturing process. And you can quantify that accurately by 3D X-ray CT, just like you could with a coordinate measurement machine. The difference between a coordinate measurement machine and CT, of course, is that you can study geometrical features that are not visible externally or cannot be accessed by either touching probes or lasers. But you can accurately quantify that, and you can compare that to a CAD model as shown here. Metrology by X-ray CT is an emerging tool, and manufacturers can now produce metrology grade CT scanners where the temperature is controlled, where you have geometric calibration with laser interferometers, and the magnification can be calibrated using special calibration samples prior to scanning. And it gives you the ability to measure certainly to within a few microns the dimensional accuracy of your component. And there are emerging standards for qualifying those measurements. So this is an area of tremendous growth at the moment, and is particularly pertinent to the study of additively manufactured components. I'm not going to go into too much detail here, but if you look at the primer I mentioned earlier, it's covered in more detail, and there have been lots and lots of papers written on the topic, particularly by a guy called Leach in Nottingham and a group in Padua in Italy. The error sources basically arise, obviously the operator, the way the operator sets up the sample is very, very important, the scan parameters and so forth. The sample itself in terms of its material, its geometry and so forth. The CT system comprising the detector, the source, the alignment of the rotation stage and so forth. The environment due to changes in temperature. and the data processing. The reconstruction methods, it is a computational reconstruction method, and so there are artifacts associated with the reconstruction process. It's not an analytical process, it's a numerical process, and there are errors that are associated with that. And so one needs to understand the contributions of all these factors when you're trying to make really accurate measurements of additively manufactured shapes and components. But I want to focus more on the defect control and mitigation by CT. We talked already about the potential for cracking. I'm going to focus more on internal defects, but obviously cracking can also be studied by CT. And the key point is that as well as measuring the external geometry with a CT scanner, you can get a picture of the internal defects, and you can get the population of defects, both in terms of their size, their shape, and their location. Why is it important? It's important because defects control a large number of properties, and perhaps one of the most important is they can lead to a very large variability in fatigue. If you look at this SN curve, which shows the dependency of the number of cycles to failure on the stress range, you can see that whilst it's true that the increasing stresses lead to shorter lifetimes, a huge scatter is observed in the data. And that is because of the presence of defects, and those defects are stochastic in nature, and so that leads to a stochastic variability in the fatigue life. So if we want to measure defects, an important question to ask, and here's an additively manufactured component, is what resolution do we need, and what setup do we need so that we can measure the defects that are most of interest. Now, of course, if you're measuring a part and you want to understand its fatigue life, then you can identify using fracture mechanics what the critical defects are likely to be, and that will enable you to set up the parameters of the scan such that you can be sure that if you when you scan, whilst you may miss some of the smaller pores, you will capture those which are likely to be critical defects and to limit the behavior of the material. And in order to do that, one has to be careful to make sure that the quality of the images are sufficient. Here you can see a single projection on the top, and at the bottom you can see a projection averaged over 8 different frames, and you can see that the noise in the top signal is significant compared to the bottom. And you can qualify that using calibration samples. Here's a simple calibration sample, and you can see that if you compare the top single projection image of those calibration samples with the bottom one, which is averaged over 8 images, you can see that you get a much better definition of those pores. And again, you can identify the conditions that you need to be sure that the defect sizes in the part are smaller than the critical defects that you would need to get a particular lifetime. It's also important to remember that, that when you process the data, you can often affect the results. Here this is actually a bone sample, but again, you can see lots of pores in this piece of bone, and you can see that when you use mean filters to improve the image quality, you can also lose information, and you can lose information about the smallest pores. And you can see that again when you apply that mean filter to the calibration sample, and you can see on the left with no mean filtering, you can see the finest defects, whereas on the right, whilst we get better definition of larger defects, we're losing the smaller defects. So setting up a CT scan requires a significant amount of thought ahead of time to work out whether you are able, using the scanner you've set up and under the conditions that you set up, are you able to measure the defects that are most of interest to you in a time efficient and cost efficient manner. So let's assume that you can you have your material, your CT scanner set up appropriately, and you can clearly see it's from these different scans that the build path and the build conditions can have a very critical effect on the distribution and location and size of the defect population. And it is possible by controlling those scanning parameters to ensure that the defects the worst defects occur in the regions where it is least likely to have a deleterious effect on the fatigue life. And we'll see later in this talk that defects that are positioned near the surface often are more likely to be critical defects. And so if you can identify build patterns that reduce the likelihood of large defects occurring near surface, that can be an important way of increasing the lifetime of your components. As we'll see, I'm sure in later talks, there are various types of defects that can be introduced when you're CT scanning. Here I just show two types of defects: a lack of fusion defect on the left, and gas pores or keyhole pores that are formed during the additively manufacturing process on the right. On the whole, the gas pores and keyhole defects tend to be circular or spherical in nature, whereas lack of fusion defects tend to be more angular, and often, if they're not appropriately, if the conditions are not appropriate, you can end up with large lack of fusion defects, which can be very important in terms of compromising the fatigue life. So it's possible using CT to understand the conditions and the relationship between the additive manufacturing conditions and the types and locations and sizes of the defects that you're introducing. Another important aspect is post additive manufactured processing, and you can see here, you can see a series of defects in I think this is an aluminium sample or titanium sample. So this is a 6-4, and you can see a range of defects, and often post additive manufactured hipping can be used to remove the defects. You can see here that upon hipping, the as manufactured pores have been closed up. But what we can also see in some cases is that when you heat treat the sample, the pores will reopen. So if I just go through those three again, you can see large pores there being largely removed by the hipping process, hot isostatic pressing, closing up those pores. But we can see that after heat treatment, you can see that some pores reopen. Now we can see that those were in the locations of the original pores if we look at particular regions of interest. So here we can see exactly the same region of interest viewed in the as-built structure, where we can see a pore of about 30-40 microns in size. We can see that after hipping, that pore has largely disappeared, but we can also see that after heat treatment, that pore has reopened, and you can see a pore, albeit somewhat smaller than the one that we started with. So it's important to understand the way in which pores can be reduced by hipping, and to make sure that those pores simply aren't just closed, but they really are removed. Of course, these defects can be critical often in terms of fatigue, and generally the microstructure, the grain structure, which is anisotropic, of course, will affect the fatigue life. But if we don't get rid of the majority of the defects can play a dominant role in shortening the life of additively manufactured parts. Often those defects occur, as you can see on the left, near the surface, and fatigue cracks will grow from near surface defects. But in addition, you also find other defects deeper inside additively manufactured parts, as you can see here. We can study the growth and the nucleation and growth of defects, of cracks from defects. And here what we can see are this is a semi-transparent view looking down on 4 additively manufactured test pieces. So what we can see here in red are the defects, so the defect distribution in each of those 4 samples. We can see a number of defects, some near the surface and some at the center. But what we can also see, because we can do a time-lapse study, we can study how those defects change over time, and you can see quite clearly with the grey contours how defects have nucleated cracks, and those cracks have grown over time. So in the top left and the bottom and the bottom left, you can see defects that have formed near the surface, and we can see how the crack has propagated from the surface. whereas in the ones on the right, we can see somewhat larger defects, but those larger defects, of course, cracks to grow in the interior. And so we can get a good understanding of crack nucleation and growth, and therefore to make fracture mechanics predictions on the fatigue life of additively manufactured parts. So if we look at the SN curve that I showed previously, the stress range against cycles to failure, if we are to image those samples, we can identify the critical defects, and you can see that when we replot those fatigue lives, showing them as a function of the critical defects, the filled samples are surface pores. The open surface, the open circle here is a subsurface pore. We can see that the lifetimes of the additively manufactured parts correlate very nicely with the size of the defects. So larger defects cause shorter fatigue lives, and we can now understand the fatigue life on the basis of the defect distribution. And we can also see that on the whole, most of the failures occur from near surface defects rather than defects in the interior. We can also understand the effect of those anisotropic defects, those loss of fusion defects that I was talking about earlier. So you can see that the gas porosity are generally spherical, but these lack of fusion defects tend to be more pancake shaped. And when we look, this is a sample which was on the left. You can see a sample where the build direction is along the tensile axis of the fatigue sample, whereas on the right we can see a sample which is loaded perpendicular to the build direction. And when we look at the critical defects, or when we look at the defect distribution, you can see that the defects when loaded parallel to the build direction are because they're pancake shaped, they present a very large cross-sectional area, whereas when you look at the ones loaded perpendicular to the build direction, the pancakes are sideways on, and because the pancakes are sideways on, they present a smaller crack area, so they're likely to be less likely to lead to fatigue failure. And that's reflected in the SN curve. So you can see here that the SN curve for samples tested loaded perpendicular to the build direction show a higher fatigue resistance than those tested parallel to the build direction. And when we plot them color coded, as we've done here, to indicate the area of the projected area of those cracks, so the Murakami's fracture mechanics predict that the fatigue strength will be related to the square root of the area of the defects. And you can see when we plot the square root of the area of those defects, you can see that the larger defects tend to be in the parallel direction, and in the perpendicular direction, the defects present a smaller area and therefore appear to give a shorter fatigue life, a longer fatigue life. If you take that into account, you can again bring all the curves. If you just plot the stress intensity factor relating to those defects, you can see that largely the differences between the parallel and perpendicular disappear, and they fall more or less onto a single curve. It's not quite true. Those loaded perpendicular show now a slightly lower fatigue resistance than those loaded parallel, and that could be to do with the grain microstructure, which is also anisotropic, and I'm sure we'll see more of that later in this meeting. And of course, if you know the distribution of defects and you're using CT to pick out those distributions of defects, you can start to make predictions about the fatigue life performance. Here you can see predicted life performance. So we have a fatigue limit of 188 megapascals, and we can see how you get a failure envelope here as the defect sizes increase. And we can see that if we compare the prediction with the measurements, you can see that most of the measurements tend to lie outside of the prediction, so that we end up with a safe life regime which can be defined in terms of the defect size and the stress intensity that's applied. We can also see that if we plot, you can see that the lifetime increases, not surprisingly, as you move towards that limit. So shorter lives indicated by red are for the larger defects, and as we decrease the defect size, you can see that the life increases towards the fatigue limit, as shown here. So I think the take-home message here is that by scanning with X-ray CT, you can plot the distribution of the defects, as you can see on the bottom. We can see that the defects present different areas in the horizontal and the vertical test directions, and those give rise to lifetime predictions that enable us to make estimates of the safe life of additively manufactured parts. And the other point to note is that, of course, in cases where you have lots of defects, you can get multiple effects. So here we can see how defects that are presented nearer to the surface tend to be the critical defects. But this modelling work just shows how defects can grow from individual defects and then join up to form larger cracks, and those multiple effects can lead to shorter lives in the final component. And again, we can see how the kind of X-ray CT data that I showed earlier can be used to validate these fatigue life crack propagation predictions. Okay, so I've taken you on given you a little bit of an introduction to the use of X-ray CT for the determination of defect microstructures in additively manufactured parts. X-ray CT is really useful because it can provide not just the external features, but the internal and the entrained defects in additively manufactured parts. AM processing can be visualized in real time by high frame rate radiography, the single images, and a great deal of information such as the cracking that Stephen showed or the defect entrainment that I showed can be picked out from real time radiography at many thousands of frames per second. Hipping, it can be effective in closing up defects, but in some cases, rather than eliminate them, they can close up and then reappear later. So you need to be really clear, and microscopy work needs to be done, and further work needs to be done to understand whether those voids have really healed themselves or whether they are simply just suppressed. The melt track patterns can have very significant effects on the number and the location of defects, and this provides a way of mitigating the effect of defects by ensuring that near surface regions in particular have low defect densities, because it's often the near surface region that is most prone to fatigue cracking. On the whole, fatigue cracks tend to grow from surface breaking defects or defects that are very close to the surface, in preference to those which are internal to the component. The scatter and fatigue properties can be largely related to the defect population. There are, of course, other factors, and grain structure, microstructure can be important, but until we can really reduce the defect population to very low levels, defects tend to control the fatigue properties. And CT can be combined with, so by obtaining the distribution of defects, you can combine that with modeling to predict fatigue lifetimes. One other point I would say is that traditionally, the kind of imaging that I've shown might take minutes or hours to undertake, but there are other ways of scanning in CT where you can combine that with production line type frequencies. So we've been working with a company who actually scan baggages, and you can imagine baggage scanners, and they can scan thousands of bags per hour. And we've been working with them to develop CT systems that will scan thousands of parts per hour. So in that case, you can scan both the external structure and the internal microstructure at a rate of about one article per second. And so there is the potential as we move forward, not just to scan research samples, but to be able to scan every sample in an additively manufactured production line. So I think there is a real interest, not just from a science and understanding viewpoint, but also from a product quality assurance viewpoint for X-ray CT. Okay, and as I was saying, fatigue generally can be better perpendicular to the build direction than parallel to it. So we need to understand better how to minimize the entrainment of defects, and in particular these loss of fusion defects, which tend to be most critical to fatigue life. Okay, I hope I've given you a bit of a primer on CT and its use in the assessment of microstructural variation in additively manufactured parts, and I'm happy to answer any questions.
Thank you very much, Philip. Very nice talk. We already have a question. Eric.
Yes, thank you, Philip, for this very nice talk. I was wondering if you have some vision about the difference between foundry process and additive manufacturing in the sense of the effect of defects, because we learn lots about foundry process, and what are for you the particularities of additive manufacturing regarding that?
Okay, that's a good question, and of course I think the key point is the fracture mechanics. The fracture mechanics approaches that have been developed for foundry and other parts are just as applicable to additively manufactured parts. The difference is, of course, that there's a tremendous propensity for defects to form, and some of those defects may have different geometries from the ones that you would have in traditional foundry products. But the basic fracture mechanics is universal. Of course, there's some really interesting factors in additively manufactured parts in terms of the microstructure and its effect on the toughness of the microstructure as well. So there are materials alloy related effects. There's obviously the ability to heat treat and to control the precipitation and second phases and so forth. But the basic fracture mechanics is the same, but one needs to have perhaps a more sophisticated understanding of the solidification kinetics and its effect on microstructure. So it's a little bit more complicated, but the basic physics is the same.
Thanks a lot, Philippe.
Thanks, Eric. Roland.
Yes, thank you very much for the presentation. I had a question on the presence of cracks. I mean, for example, those ones that Stephen described in nickel-based alloys. So in additive manufacturing, very often you have these little cracks, which besides not only are small, but can be in zones where you have compressive residual stresses. If you are a little bit away from the external surfaces. So I'm just wondering if you have any clue on how to identify those defects, because clearly they would play a role, for example, in fatigue life of these materials.
I mean, I think that's a really good point, and we haven't really discussed residual stresses yet, but obviously the kind of work that Stephen was showing following the cooling, you can evaluate some of the residual stresses as you cool the sample. So I think this is an area that's going to become more and more important as we improve our manufacturing processes. As you say, I mean, if you have obviously X-ray imaging is such that if you have a crack which is closed, you cannot see the crack by X-ray imaging. There are ways you can enhance it. So Stephen mentioned phase contrast, and synchrotron X-rays are fairly coherent. You can also do phase contrast in the lab, and you can use phase contrast to increase the detectability of cracks, so that you may get a little bit of phase contrast, which has a coarser resolution than the resolution required for to understand the crack. It's to see the crack in absorption imaging. So certainly you can do that. One of the other things, I mean, obviously the work we showed where I showed the crack growing, we were also imaging under load. So if you image under load, that will also tend to open cracks. So you can increase the detectability by by applying a small holding load to hold the cracks open. So that can be another way. Another thing you can try is to use region of interest. And region of interest X-ray imaging allows you to obtain higher resolution on a smaller region of the part. So if there's a particular area where you're concerned where the stresses are at their largest, you could use X-ray imaging to try and increase the resolution. But clearly there is a limitation in the resolution that you can obtain. And if cracks are held really tight shut, you won't see them.
Thank you. Thank you very much.
Thanks, Roland. Any more questions? Okay, maybe. So I have a generic question that perhaps also is pertinent to what Stephen discussed before. If I look at things from a modeling perspective, the information that you get now is highly resolved in time and in space. So how far or how close are we to deducing kinetic laws of solidification for solid state phase transformations or crack formation or other defect formations down at that length scale?
Well, maybe that's a question we should answer at the end of this meeting rather than the beginning. However, I think it's a really good one. And of course, I think the point that Stephen made really vividly is that there's all sorts of information we can now get. Of course, we focus so far on X-ray imaging, but there's the electron microscopy as well, of course. And a lot of it will hold information about kinetics and the chemistry that is taking place during the solidification. So I think there's some really exciting X-ray imaging techniques now that will allow you to monitor the segregation, the changes in lattice spacing, the residual stresses, the phase transformations. So that I think there are lots and lots of tools if we can put them together, we can start to really test and validate the models that you're talking about, even at those very high resolution scales in terms of time and space that you need. So I think maybe we should come back to that question later, but
yes,
I think there are a number of good techniques that can at least help to validate those models.
Okay, great. Okay, thank you, Philip. Thank you very much.